This is part 3 of the airfoil section of Aeronautical Engineering. At the last part of part 2, we calculated where the aerodynamic center is on a particular airfoil, a NACA 2312. We were shown this graph which gave us all these numbers, that the center pressure is at 27%. Ooh, let me get that on the screen. Yeah, center pressure was at 27% of the distance between the leading edge to the trailing edge for a high angle of attack, an 18-degree angle of attack. We were told it was at 35% of the way back from the leading edge to the trailing edge at a lower angle of attack, 3 degrees. We were told that the coefficient of lift is 0.35 at the lower 3-degree angle of attack, and that the coefficient of lift is 1.44 at the greater 18-degree angle of attack. So we just called the position of the center of pressure X, and we calculated that the center of pressure should be around 24-25% of the way back from the leading point of the wing to the trailing point of the wing. Okay, the aerodynamic center is a good place to put the center of gravity of an airplane. Notice I did not say the center of pressure, I said center of gravity. We've talked about 3 different centers so far: the center of pressure, the center of gravity, and the aerodynamic center. Okay, the center of gravity should be in front of the center of pressure. This is what gives the airplane stability. So the tail pushes down on the back of the airplane because center of gravity is in front of where the wing is lifting. Okay, here are a couple of airfoils. Well, same airfoil, let's assume, but at 2 different angles of attack. This one, we'll say it's at a 3-degree angle of attack. We'll say this one's at an 18-degree angle of attack. As you can see at this slide angle of attack, the aerodynamic center is at 24% of the chord, 24% of the way back from the leading point to the trailing point. And the aerodynamic center on this one is also at the same place, 24%. But notice at the center of pressure, it's further back at the slide angle of attack than it is at the greater angle of attack. Here it's at 35% of the chord, and when the angle of attack is 18 degrees, it's only at 27% of the chord. Okay, the lift coefficient, CL, C means coefficient, little l next to it means lift, as opposed to CD, drag coefficient. Okay, the lift coefficient is greater at this greater angle of attack. As we looked at earlier, it was 1.44 for the 18 degrees, it was 0.35 for the 3 degrees. The distance between the aerodynamic center and the center of pressure is less. Yep, not much distance there, a lot of distance there. Okay, the product means one thing times multiplied times another thing. Okay, of the lift coefficient times the distance between the center of pressure and the aerodynamic center stays the same. Okay, the pitching moments stay the same. By definition, that's what an aerodynamic center is, the point at which the pitching moments are a constant. Okay, regardless of the angle of attack. The lesson to be learned here is that the center of pressure of a cambered wing moves such that the wing by itself is unstable. A cambered wing requires a tail to give it stability. If it doesn't have a tail, the wing will pitch up at high angles of attack and pitch down at low angles of attack. It'll always either pitch down and then pitch down more and dive, or it'll pitch up more and stall. That's how wings without tails do, or cambered wings without tails. But here's a wing that won't do that. This is a reflexed wing. the center of pressure of a reflexed wing moves forward at low angles of attack. In other words, when it's like this, the center of pressure is here. But if the angle of attack increases, the center of pressure moves more toward the back, just the opposite of the way it does with a cambered wing. A reflexed wing is positively cambered for about the first 75%. See our camber line here? The camber line is always halfway between the top of the wing and the bottom of the wing, no matter where it is. That distance equals that distance. That distance equals that distance. That distance equals that distance. Camber line's always halfway between the top and the bottom. Coincides with the chord at the beginning and the end, but not necessarily all the way along. Okay, with a reflex wing, the camber line curves up above the chord line for about the first 75% of the chord. Then it dips down below the chord line for the last 25%. And as you can see, this would kind of flip the air back up a little bit, or not let it be thrown down quite so much as it goes past the back of the wing. And as this wing pitches up, you can see why it would lift pretty good back here, and as it pitches down, you can see how this would act kind of like the elevator on an airplane and not give you so much lift at the back of the wing. In other words, make the center of pressure move forward as this angle of attack isn't much, and backward as this angle of attack increases. A reflex wing needs no tailplane. It pitches up at low angles of attack and pitches down at high angles of attack. If the angle of attack at the wingtip, okay, now we're talking about washout. If the angle of attack at the wingtip, here's a wing we've drawn. It's got a dotted line there because you can't see the bottom of the wing. We're looking at it from the top of the wing, looking at it from the tip end. There's the wing tip, there's the wing root. We drew it kind of short, but you can imagine it'd be a lot longer. Okay, if the angle of attack at the wing tip, see our angle of attack, that dotted line's not very far away from that dotted line, but yet this dotted line shows a greater angle of attack for the root. Okay, when the tip has a smaller angle of attack than the root has, then you have what is called washout. Some airplanes don't have any washout. Some have a good bit of washout. Spoke to a fellow a while back. He's manufacturing an airplane that has 10 degrees of washout. I asked him why, and he said that way he can, if he gets caught in a cloud, he can pull the yoke all the way back, give it full power, and he's guaranteed to descend at a slight enough speed that he won't get killed when he crashes. But anyway, generally 2 or 3 degrees of washout is what you normally see on an airplane wing. Uh-oh. Sorry about bumping the camera there. Okay. Washout ensures that the tips will be the last parts of the wing to stall. The roots will stall first because they have a higher angle of attack. When the angle of attack at the tip is 10 degrees and the angle of attack at the root is 13, the root is closer to the stall angle than the tip is. This feature enables the pilot to control the airplane further into a stall and regain control earlier when coming out of a stall. Let's look at the swept back wing with washout. So there's a jetliner I drew here. Had to make this wing a little longer, so I stuck that there and didn't have me any white out for that little line there. But imagine this is a jetliner and you're looking at it from up above it in a helicopter. Okay, as you can see, the wings are swept back, plus they also have washout because the tips are pointed down a little compared to the roots. Okay, see there's the higher angle of attack at the root. There's the lower angle of attack at the tip. This is a side view. This is a plan view, they call it. Plan means looking at it from the top. Okay. As you can see, the angle of attack at the wing root is greater than the angle of attack at the wing tip. The root of the wing obviously lifts more toward the front of the airplane, because the root of the wing is located more forward, is closer to the front. The wing tips are more even with the back of the airplane. So, okay, the root of the wing obviously lifts more toward the front of the airplane. The tip lifts more toward the back of the airplane. This feature causes the plane to pitch down after stalling, because the roots stall first and the tips stall last. Okay, if a wing's... Okay, now we're going to talk about dihedral. Here's a little airplane. Let's imagine this plane flying at us. There's the propeller. It's coming toward us. Notice it has a lot of dihedral. This wing goes up. Looks like a sky pup, little airplane I saw years ago. The tips are a lot higher than where the root attaches to the fuselage. Okay, if a wing's tip is higher than its root, the wing has dihedral. Some high-wing airplanes have no dihedral, but most typically have a few degrees of dihedral. Low-wing airplanes generally have many degrees of dihedral. This extra dihedral associated with low-wing planes makes the airplane's center of gravity not so high above the wing. See here, if you had a lot of dihedral where it looks like a V instead of a straight line across there, and if this were a low-wing airplane with a fuselage up here, you can see that having the wings go up makes it where the center of gravity isn't so much higher than the wing itself. And you don't want that center of gravity much higher than the wing. The lower you can get it, the better, because the higher it is, the more forward it must be placed in order to have stability. Okay, that's a long enough lesson. We'll take up here on the next one. That was part 3 of Airfoils, Aeronautical Engineering. Catch you later.